Assalamualaikum and good afternoon.
Waalaikumsalam.
Okay, are you still there?
Yes, Professor.
Okay, so I think you already here. You already know to solve this one, don't you?
Actually, no.
Huh?
Actually, no.
No, I mean, so in your undergraduate study, did you solve a boundary layer like this?
Actually, doctor, I'm not sure because it's very long time.
Okay, so it's okay. So we will go through back again this solution in our tutorial. So this is just the uh, the idea, the notes part. Okay. Okay, Assalamualaikum and good afternoon. So we continue our lecture on the theoretical of boundary layers. So in previous lecture, we are focusing on calculation of delta boundary layer thickness, local drag coefficient, and also the drag coefficient of this one with this five velocity distribution. And I hope you could do this as your homework, because this five velocity distribution is actually the most common velocity distribution to describe the velocity behavior for laminar boundary layer. So another things that you need to know is the Blasius exact solution. So Blasius exact solution is introduced by one scientist named Blasius, and why it take why the solution of his called an exact solution. It is because, so for our calculation here, okay, if you notice, so previously we say that the boundary layer is actually the y-axis, the distance in y-axis. So from u equal to 0 until u equal to 0.99 capital U, means 99% from the free stream velocity. However, we did not use any term of this in our calculation. So it means that von Karman, what we learned previously, the von Karman equation actually and not use the idea of 99%. So it lump sum, so it's round up the value. So it just take the condition of U equal capital U. So it just assume that it is not 99%. So let's take the boundary is U equal 100% of capital U. That's why we don't have any 99% in our calculation. Okay, that's why von Karman is actually the estimation method. Okay, but it's still correct. Okay, so for Blasius, okay, Blasius they will use exactly 99%. That's why we call the Blasius solution here is Blasius exact solution. Okay, and then from the Blasius exact, so Blasius is a okay. So now we will discuss about the Blasius exact solution. So Blasius exact solution is actually come from the Navier-Stokes equation. So it puts all the things, the simplified, integrate, and so on and so forth. But it is I'm not showing you the derivation here. Okay, so I'm not sure whether I need to ask this as your assignment or not. Okay. Say to simplify this one, okay, so finally the Blasius proposed the term of this one from the Navier-Stokes equation. So some textbooks will have this term with the f prime here. We have f and f prime, and we have f double prime and f triple prime here. So the word the meaning of prime here is actually the differential terms. So we have f double prime here is d square f d eta square, and f triple prime here is d 3f over d eta cube as this one. Okay, so this is just what you should know, okay, because blast years is not easy to solve in written examination. So means in the final exam, whether it is before COVID or after COVID, so it is not easy to ask student uh, for blast years index solution, because it needs actually it's depend on what you start. Okay, but if I would like to ask you about the blast years exact solution, it might be exactly like this one, because I need to supply you a set of data. Okay. So and then assumption. So we assume that f equal f eta, and f double prime is the double integral differential of f eta, and the f triple prime is the third three differential form of eta. So what is eta? So eta is actually reflect the velocity distribution. So here, so it is written as eta is equal y square root u rho mu x, or y equal u over nu x. Okay, so this is actually the eta here is the velocity distribution. So the group here, the terms here is quite complex, because as I said, it's come from the Navier-Stokes equation. As you know, in Navier-Stokes equation, we have terms of density, we have term of mu, and so on and so forth. So it's come from that one. Okay, that's why uh, it is okay for you to take this to make notes for this chapter from my video later on. Okay, so this is the assumption of the Blasius exact solution. So then, as I said, it is not easy to solve this, to give this as your final your question, because it is actually the data must come from the experimental or the analytical. So means you have a set of equation. You have a set of equation comes from your Navier-Stokes equation, and then you will give the location, the value of y, because you know we have a flat a flat plate like this, and you have the boundary layer occur like this one, and then you will give a lot of value of y here, and then you will vary it with value of x, and then you will get a lot of velocity data. Okay, and then okay, we start with eta here. Okay, we assume that eta is equal y square root u nu x. So the y here is actually reflect the y axis here. Okay, so and then you just give eta is equal to 0, 0.1. The more specific numbers, okay, make your answer more precise. Okay, but usually if you get this question in your final exam or your test, say we will provide you the basic equation of this one and also the assumption of this one. No worries. Okay, but you need to do is you need to know the tricks to calculate this. Okay, and the table here is also will be given to in if this question being asked in your test, because all these equation is actually come from the analytical. So meaning you put the axis, the value of x and y, and then you get the value. And the assumption of this one, you may refer to the uh, this assumption. Okay, so and then from this table, okay, from the experimental, the analytical value, so we substitute the value of, you get this table. Okay, and then from this table, normally you will be asked to calculate what is the value of delta, what is the value of local drag coefficient and the drag coefficient. So first step, what you need to do is you need to find the location where the U is 0.99 capital U, because this is reflect of 99% of free stream velocity. First, you need to determine where the 99% location. So where you want to do this is, okay, means that from this equation, okay, you could rearrange this equation become u over capital U is equal to 0.99. So you need to find where is this data or this point was is located. So from this table, we know that the f prime here is equal to u over u. So, and then from this column, you need to find the nearest value to the 99% here. Okay, so means that, so this column is reflect u over u. So, and then, okay, you need to find the nearest value to the 99%. So here we have 0.9916, 0.9969, 90, 97, 99, and 1.0. So you need to find a location or a data, a set of data which is the closest value to the 99%. So from here we could say that 0.9916 is the closest data to the 99%. Please choose this one because we stick to the definition that boundary layers is actually occur until 99% of free stream velocity. Okay, so if you take 0.69, 90, 97, and so on, you actually choosing value which is nearest to 1, which is nearest to 100%. No, please choose value which is nearest to 99%. So from this table, it is 0.9916. So that's why I said previously. So if you have a lot of data or you are doing your master project with this idea, okay, it is better for you to give more accurate number here because you will get might be here is 0.999916. So it is more closest to the 0.99%. Okay. And 0.99016 or 01 and so on. You need to find the closest point to 99%. Okay, then after you get that point, what you need to do is what you need to do is you need to see all the value here because all these numbers will be used in the next calculation because we are calculating the condition of boundary layer. Okay, so now as I said, so we take U is 99% of capital U, and at that time we assume that Y is equal to delta. So this is the our real condition of boundary layer, our real exact definition of our boundary layer. So, and then from the table, we could get that the f prime is 0.99 and the nearest value is 0.0991612. So, and then the value of eta is equal to 5. So next, what you need to do is, because we know the eta is assumed as y square root u over nu x, so we could substitute the value of 5 here. We have 5 equal delta square root u over nu x. And then, so I think you already know the relation of real number here. So we substitute the real naught over x is equal u over nu. So we could substitute these terms. Okay, so we replace the u over nu here with a real number. And then we could solve this one. So we could get that delta is equal to 5x over square root real naught. Reynolds number. So that's why in this table, we say that for Blasius exact solution, the value of delta is equal to 5x over Reynolds number. And this value is okay for you to be remembered. So you need to, it is better for you to remember this one, because if you have boundary layer problems and you don't know what is the velocity distribution for your boundary layer, it is okay for you to assume that your boundary layer is laminar. If that laminar, after that we will in tutorial we will show how to determine whether it is laminar or turbulent. So if you assume that your boundary layer is laminar and you don't know what is your velocity distribution, so it is okay for you to take to assume that your laminar boundary layer is your laminar layer is fulfill the Blasius exact solution. So means that you just take you just use 5x over Reynolds number to calculate the boundary layer thickness, and you use the 1.328 to calculate the drag coefficient. Okay, but if you know the velocity distribution is by the power of 2, 3, and 4, so it is you need to use this value. Okay. Okay, so this is the way how to determine the value of delta, and then we need to okay, we go step by step. We need to determine the value of delta star. So we know that delta star is the equation is integral of this one over u minus u over u dy, and from the table we know that u over u here is equal to f prime. So and then we need to replace. So if we replace the value of u here, okay, so the problem of this equation is actually not can be used straightforward with the Blasius solution. It is because, so if we replace the u over u here with the f here, the value of f here is actually in term of eta, but this equation is in dy. So we need to do some modification. So let's say we have eta is equal y square root u over nu x, and then we have d eta dy, so we have u over nu x, and then we could change the value of dy here becomes d eta nu x over u square root. So that's why we need to change here, because the f prime here is actually function in eta. So we need to change the dy here also with the function of eta. And then from this calculation, we substitute the value of dy here with this term. So now the delta star equation, okay, from 1 minus u over u dy is changed into this one. And then what we need to do is we need to integrate this term from limit from 0 to 5. Okay, limit here 0 to delta, because in term of dy, so the boundary layer is occur from 0 and from y equal to delta. But if we change the axis, mean we are not using y, we are using eta. So the limit is actually occur from 0 to 5. So where we get the 5? Because from this table, we found that eta here, the boundary layer is occur from the 0 to the number of 5 here from your analytical result. So the number 5 there is actually the constant one. So and then to solve this one, we could take out the value of nu x over u because it is constant, and then we could separate the terms to ease our calculation. So we have the integral of 1 and d eta from here, and we have the integral of f prime d eta. So the integral of 1 here to eta will give us eta, and the limit is 0, and the limit is 0 to 5. And the integral of f prime mean f, as I said, f prime means the differential form. So the integration of the differential form will give us its own state. So it will become fn here. And then no, fn f eta, function of eta. So the integral here will change the differential form. Okay, I think you understand this one. So we have the f eta and the limit is 5 to 0. Then what you need to understand here, we cannot solve this problem by using the normal integration because we need to base on our analytical table. So for this one, it's okay because we only have one term with it, which is eta. So we have eta, if we substitute with the limit 5 to 0, so we get 5 here. So and then from function of eta, so if we substitute the value of 5 and 0, so we will get 3.2834. So from where we get this one? So we not solve this one by using normal integration step. So we need to refer to our table. So in our table here, so we have f eta here. So we have f eta, at eta equal to 0 is equal to 0, and at eta is equal to 5, it's equal to 5. It's equal to 3.2834. So integral, we need to subtract. So we subtract 3.2 with 0, so we get 3.2834. That's why we write here the value of this one is 5. Okay, and the value of this one is 3.2834. And then we solve this one, so we get this value 1.7166 for delta star. And then we know that the delta here, okay, if we substitute, we could write nu x over u is equal delta over 5. So we substitute in this equation, so we will get the delta star is 1.7166 x over square root Reynolds number. So and then if we calculate the momentum thickness theta, so again the common equation is show like this. So we need to change because this equation is actually based on y-axis, so we need to change into eta. So I think you know how to change this based on the previous explanation. So now we have the integral 0.5 with f prime times 1 minus f prime and the eta. So here again, we are not solve this one by using the idea of normal integration. So we must base on our data from our analytical calculation previously. So what is the meaning of this one? So we know that integral here means the summation. Okay, the summation so means we could change the terms, the idea of integral with the idea of sigma. Mean we need to calculate all of them and then we add all the values. Okay, so we change the terms integral here with the sigma, and then we know here that nu x over u can be replaced with delta over 5. So I showed this on the previous calculation. So and then we need to find the value of f prime 1 minus f prime, and we multiply the value with the delta eta. Okay, the best way is we create a table. Okay, so let's say we have an eta here. So we have f prime and we have f prime times 1 minus f prime times eta. So eta here, so we found that we have eta 0, 0.51, 1.5. So it's taken from the table. So we have this one 0, 0.51 and until 5. So we take that all the value. So we have 0, 0.51 and so on until number 5. So, and then we take all the value of f prime. So we can have 0.1659. So if we see here, so we have f prime. So the 1659 until 991.716. So we take all this data and then we put in this table. Okay, so we have this one. And then we could solve the equation here based on the meaning of this equation. So means that we need to multiply the value of f prime with the value of 1 minus f prime with the value of delta eta. So and then what we do is, so we have f prime here 0, 1 minus f prime, so we have 1 minus 0, and then we time with delta eta. So delta eta means the difference between one point to another eta. So if you see the interval gap here, it is equal to 0.5. So means that the delta eta here is actually constant at 0.5. Okay, and then you calculate all of these. So and then you need to understand that the integration means the total summation. So it's equal to sigma, means you calculate all the points and then you add all of them. So you add all of this one, you will get 0.6548. So means that this value now is equal 0.5648. So and then we substitute the value of delta here with the 5x over square root Renault, and then we get it is around 0.6548x over square root of Renault number. Okay, so and then if you read a textbook about the Blasius number, it is normally assumed that the value of theta is equal 0.664x square over square root Reynolds number. So it is because, so the difference of value here, not because our calculation is wrong. So it is because our data that we have here in this table is actually not precise. So we just take a very big gap, actually 0.5. So that's why they give us the value of delta uh, a little bit different compared to the official value of theta from the Blasius exact solution. So and then we calculate the shear stress. So so from here, so we have df d eta is equal u over u, and it is also f prime. So I'm sorry, the actually df prime for the function of eta. So we have, this is the big bracket. So and then we could say that small u is actually capital U times f prime. And then if we differentiate this one, du d eta, so it will become u df, because we have d eta. So we cancel the value of d eta. Okay, so and then from these terms we could change from eta here. So we have d eta dy with square root u over nu x. So and then we have the Newton law of viscosity. Tau is equal mu du dy, y equal to 0. And to simplify the value of du here, so we write as du d eta times d eta dy. And the eta is still equal to 0. So and then we need to solve this equation. So we substitute with all the terms that we prepared previously. So we have this one and this one. And then we could finally write, we substitute with the value of f prime at eta equal to 0. So here again, so we take the value from our table. So it is equal to 0.3321. So if you see this table, you will find that the f eta at the eta equal to 0, it is 0.3321. So means that you substitute the value 0.3321 and you will get the value of tau now is equal to 0.3321 rho u square over square root Renault. So you could calculate the local friction coefficient as von Karman steps previously. So we have tau over 1 over 2 rho u square. So we substitute the value and then we could get the value of CD of this one. And then we could calculate the drag coefficient. Okay, we could calculate the drag coefficient here. So this is a little bit simplification for the calculation. So we know that the F, this is the drag force, the FD. So and then this is the terms from the equation. So we have 1 over 2 rho u square A, and then this area is actually B times L. So I already explained about this. So and then we know that the shear stress here can be written in von Karman terms. So von Karman is equal to rho u square d theta dx. So what we means that we could write that equation as shown like this. So we have rho u square d theta dx. So we have b and dx. So and then we could simplify. We could cancel all the terms here. For example, b and this b and so on and so forth. So finally, we could say that CD is actually just 2 theta over L. So and then previously we calculate the theta, so it is equal to 0.65. So we substitute into this theta and we could say that the drag coefficient is 1.3096 over square root of Reynolds number. Okay, so in Bohr-Karman solution, you also could use you also could calculate the value of CD by using this equation. 2 theta over L. So this is the simple equation to calculate the value of CD. So and however, if you see the value, okay, it is so what we calculate is around 1.3096, but the official value of Blasius exact solution is 1.328 over square root Reynolds. It is because our value of theta is actually not the same. So again, it is not because we are doing wrong. It is because the data that we have is a little bit limited. So the interval value is high. So we get a little bit tolerance compared with the official value of Blasius exact solution.